Hello. Hello, good evening.
Evening, sir.
Hello, good evening, Professor Abhishek. This is Parth Joshi.
Hello, Parth, can you hear me? Hello,
Yes, sir.
can you share your screen?
Yeah, sure.
Okay.
Sir, I have shared my screen, so can you please confirm whether it is visible?
Yes, I can see your screen. I can see. Can you change the slides? Yes, yes, I can see the change in the slide. Okay, so we can start now. Let me introduce Parth. Currently, Parth is working as a research scholar in IIT Bombay. So now he will be delivering some sessions on transmissions. Now I will hand over the session to Parth. Parth, you can continue.
Sure, sir. Thank you. I am just trying to share my video. So please let me know whether you can see that. So I'm sharing my video. So can everyone see me? Hello.
Yes, sir. We can see.
Okay. Sure. So hi everyone. Good evening. So my name is Parth Joshi. So I'm basically a PhD student of mechanical engineering at IIT Bombay, and I have been awarded the Prime Minister's Research Fellowship to pursue my PhD program at IIT Bombay. And as a part of this, I have got this opportunity to discuss with you on this topic of EV transmissions. So So I'll just begin with a small introduction about myself. So basically, I belong to Pune. I did my undergraduate studies at BITS Pilani Goa campus in mechanical engineering. Um, in my last year, I did my internship at Tata Motors Pimpri factory. Then, so that like from that time onwards, I have been interested in the automotive field. Then I worked for 1 year at SKF Bearings in Pune and Bangalore factory for about 1 year. And then after that, I decided to pursue masters. So I did my MTech in engineering design at IIT Bombay, and so I selected design as my specialization, and in that I did my MTech thesis on uh, control of hybrid electric vehicles. Basically, I did some simulation studies. So I investigated how we can get some fuel economy improvements by converting like basically Tata is kind of small trucks into hybrid vehicles. What is the possible fuel economy benefit that we can get? So that was my topic of my MTech thesis, and I was awarded the Tata Fellowship at that time. So that's how I actually picked up interest in electric and hybrid electric vehicles, where I worked on several projects related to that. Then I at the end of my final year, I got a campus placement offer, and I started working at Eaton Technologies in Pune. I worked for about 2.5 years, and my work was again related to uh, electric and hybrid electric vehicles. And there I actually focused on the automotive transmissions part. I did some simulation studies for for evaluating different concepts of electric and hybrid electric vehicles, different concepts of transmissions. Uh, and then after 2.5 years, I decided to pursue a full-time PhD program. So I left my job at Eton, and then I joined this PhD program at IIT Bombay last year in January 2021. So, so that's about myself. So I hope you find this session interesting. Uh, so in today's lecture, I'll be just sharing some insights related to so today's lecture will be very basic and introductory, and I hope you enjoy this session and you find it interesting. So please feel free to ask any questions or at any point of time. So if you have any question, please do feel free to ask any question. And if you want to share any comments or anything, so please feel free to do so. So let's begin uh, this session. So I'll start with the presentation right now. So before we begin, so I just wanted to know about uh, like the class, so what backgrounds are like all of you from, um, and like I just wanted to know like with what motivation have you taken this subject? Like if some of you can just share that. Hello.
Hello.
Yes. Yeah. Please go ahead.
So by subject, do you mean electric mobility?
Yeah. Yeah.
Yes, sir. Sir.
Yes.
It's actually uh, most of us are like interested in keen on improving efficiency of vehicles as such.
Okay.
So we found it easy. we found it interesting that electric vehicles are way more efficient than conventional ICE engine vehicles in
Right.
terms of their tank to wheel efficiency. So
Sure.
that is what attracted us to electric vehicles, and it is also clean energy. So
Right.
we would like to add to the future technology.
Okay. Sure. Sure. Right. Thanks. So you are Sumedh, right?
Yes, sir.
Yeah. So you are in which year of your program?
So this is a 1 year program. So it's the first year, sir.
Okay. So you are BTech or MTech?
There are some
Yes,
students
sir.
from MTech and some from PGDEM.
Sure.
We have
Okay.
invited them to attend your lecture along with honors course students.
Okay. Great.
So we have yes, so we have three kind of students. One from MTech Automotive, some from PGDM course, which is post graduation diploma in electric mobility, and
Sure.
some are from the honors course.
Okay, sir. Okay. Sure. Uh, Yeah, thank you, sir. So this basically, I just wanted to know the background and the overall level of awareness of the students so that like we can improve the content and everything like as we go along. So in today's session, I'll just try to give you a brief overview of the importance of electric vehicles in the current Indian scenario. Uh, Yeah, so all of you are aware, like every day, the electric vehicles are in the news, and every other day we hear some of the other news related to either a new product launch or some new announcement of the government related to some new policy changes. So basically, as our Honorable Prime Minister has said, the world is now in the middle of a new mobility revolution. Uh, so basically the way we are traveling, the way we go from one place to the other is changing rapidly. And also, as Shri Amitabh Kant, who is the CEO of Niti Aayog, has rightly said that this shift towards electric mobility is inevitable. So the world is now moving towards new modes of transportation which were probably not thought of earlier. So which involved like concepts like shared transportation, pure electric, uh, which may or may not involve like road transport or air, like through the air or whatever. So different modes of transport are being explored, and so and so India is also part of this new mobility revolution. So let's try to see uh, what all things what are the like, key issues that are being faced by the country currently, and how are electric vehicles important in this context. So, so as a background, uh, so we can see that India is basically the fifth largest automobiles market in the world. So about 3.82 million units are sold in 2019. So which is a huge number. Uh, so in India, the transport sector is one of the largest user of oil in India. It accounts for about one third of the crude oil consumption of the country. And out of this share, so 80% of the share goes to road transport itself. And the transport sector is the second largest source of CO2 emissions globally. So, uh, so the transport sector is responsible for substantial amount of greenhouse gas emissions, which has an adverse impact on climate and leads to global warming. So we'll see that issue later. So because of the factors like the growth in urbanization and the increase in per capita income and the overall improvement in the economy, uh, the vehicle demand has always been on the increase. So normally we see that people buy mostly conventional vehicles. Until now, electric vehicles or like alternative fuel vehicles were not available. So currently, conventional vehicles are like accounting for about 97% of the vehicle sales. So that was the figure in financial year 2019. Uh, so if we continue to have this uh, substantial share of conventional vehicles, so it poses some risks. So the conventional vehicles rely mostly on petrol and diesel. Uh, so they basically so the crude oil that which is basically from which the petrol and diesel are derived from. So it's mostly imported in India, and so the amount of production which is so the domestic production is quite small. Uh, so there are energy security concerns with the rising amount of imports of oil. So there is a huge amount of expenditure that the country of the country every year on oil imports. And also due to global events, the oil price keeps on fluctuating. So as of all of us are aware, like the current Russia-Ukraine crisis, so that is likely to increase oil prices significantly. So then uh, that would actually have a hit on India as well. And it is like very likely that the petrol and diesel prices are going to increase quite a bit. So they are already above 100 rupees per liter. So uh, and also because these conventional vehicles contribute to a lot of greenhouse gas emissions, so that would also pose a significant risk to the climate change. So all of us are aware of this issue of global warming. So the, the global annual average temperatures have been showing an increasing trend since the last several decades, and the last few decades have been experiencing like a very rapid range in rapid rate of increase in the temperature. So basically the transport sector is one of the major contributors towards the increasing amount of CO2 emissions. So the global warming is mainly because of heat trapping gases like carbon dioxide or methane. So they trap the heat and they do not allow the heat to escape from the atmosphere and reflects the heat back to the Earth's surface, and that actually causes the increase in the temperature on the Earth's surface. So because of the transport sector, uh, so as we can see on the pie chart over here, the road transport is like considering including cars, buses, and trucks and all these things. So total about 75% of the total emissions associated to the transport sector are from the road transport itself. So road transport is a significant contributor to the overall uh, transport sector associated emissions. So if we see the trends in the fossil fuel like related CO2 emissions, so we can see this chart so for several regions around the world. So especially for India, if we observe that although the overall amount of CO2 emissions are much lesser than the other regions of the world, still we can see that the rate of increase in the CO2 emissions has been one of the highest which can be observed as compared to any other regions of the world. So, uh, and because the transport sector is a significant contributor in this issue, so some alternative source of energy has to be looked at so as to curb these emissions. So if we look at the issue of air pollution, uh, so the pollution level in India has been witnessing an alarming rate. So India was ranked around like about fifth in the world's most polluted countries, uh, as the statistics by IQ Air have been reporting. And so among the most polluted cities, so six out of the first top 10 were in India. And if we look at the rankings by AQI, so if we see the 2021 rankings, So India was the ninth most polluted country in the world, and if you look at the top 50 most polluted cities, so 43 Indian cities were among the world's top 50. So we can see that the overall air quality in India has been becoming worse and worse every day. So if we look at the snapshot of air quality, so this I just captured it today from the AQI dashboard. So see, if we look at the Pune Air Quality Index, it is in the severe range. So this was in today afternoon. So one of the major pollutants which are contributing towards this are like particulate matter 2.5 and 10 micron size. So this is so transport is because there are huge number of private vehicles in Pune because of the public transport and currently because there is a lot of metro related construction going on, so there is a lot of traffic congestion in the city. So we can see that that is being reflected in the air quality. So the construction work is causing traffic congestion, and that's why the transport related emissions are very high in the city. So if we look at the oil and natural gas availability, like the domestic availability for India, uh, so the so in India has very little share of oil reserves and natural gas reserves. So they are about just 0.3% of the global oil reserves, and the natural gas reserves are as small as 0.7% as compared to the global reserves. And if we see the trend in terms of the availability, it has been largely declining over the years. So there is a lot of dependency of India on. So India has to import crude oil and natural gas substantially. So if we look at the figures, like if we compare the amount of production and import, uh, so so the production of oil, if we compare between financial year 2013 and 19, so the production has actually gone down, whereas the import has increased substantially. So the import dependency has increased from about 84% to 88%. Um, Whereas for natural gas, we see that it has increased from 23% to 36%. So oil and natural gas are both essential for producing the fuels required for like petrol and diesel. So then the oil import bill has been always on the rise. Uh, and so if we see for financial year 19, so only 12% of the overall crude oil demand was met by domestic production, and for natural gas it was just 64%. So yeah, so as we have seen, like the issues of basically the increased amount of dependency of the country on conventional fossil fuels, and so basically if we see that if we have high conventional vehicles in the way ahead, so then the amount of import bill will keep on increasing, and also the greenhouse gas emissions would increasing. So India, as a part of India's commitment to mitigate this issue, so India signed the 2015 Paris Agreement. So in the Conference of Parties, so India has pledged to reduce its carbon footprint uh, by 33 to 35% by 2030 to levels about basically to reduce its carbon footprint to levels about which were there around 2005. It has also pledged to increase the share of non-fossil fuels based electricity to about 40% by 2030. And also India has set a target to reach about 30% of EV electric vehicle sales by 2030 in the largely in the passenger cars segment. So, so as if we see the way ahead, so it seems that electric vehicles is a promising pathway because it's a clean, it uses electricity, which is a clean energy, and so it's a promising pathway to increase energy security and reduce the country's dependence on oil imports, and also to lower the carbon dioxide emissions, and also to improve the air quality in Indian cities. So therefore, the government of India has identified electric mobility as a key area of focus for further development. And the government has been pushing this for electric mobility uh, in personal vehicles as well as public transport through several initiatives. So if we look at the possible technology options which are like clean or like which involve like zero carbon footprint or low carbon footprint kind of technology. So we can categorize them as electric mobility uh, or low carbon technology. So so low carbon technology would comprise of fuels like CNG or LPG, uh, or methanol or ethanol. So these kind of fuels, alternative fuels which are derived from uh, more sustainable sources, or they come like give rise to lesser emissions as compared to the petrol or diesel kind of fuels. Uh, and we also have other options like battery powered vehicles or fuel cell powered vehicles. So currently, since the last few years, we have seen that the government is mostly looking at battery powered vehicles. So so as a part of this transformation into electric mobility. So Niti Aayog has proposed a new mobility paradigm which involves like shared, electric and connected as the new mobility paradigm, which involves like larger amount of shared transportation, which involves like using large amount of public transport as well as instead of using personally owned vehicles, using more of shared vehicles, and also more of electric vehicles, so which will be focusing mainly on, and also connected vehicles, so by using artificial intelligence and these kind of technologies to basically draw like use data and derive meaning out of it to do some like develop useful solutions, and uh, also to make uh, the systems like mobility related systems more efficient. So the government of India has been taking up several initiatives starting from 2011 when they uh, launched the National Council for Electric Mobility, and in around 2014 uh, they launched the National Electric Mobility Mission Plan uh, for 2020, where they defined several initiatives. So in around 2016 or so, uh, the phase one of the FAME India scheme. So FAME stands for Faster Adoption and Manufacturing of Electric and Hybrid Electric Vehicles. So that was a scheme to incentivize the purchase of electric and hybrid electric vehicles. So this scheme was not very successful, but it provided some initial momentum, uh, and then later on around 2018 or 2019, the government launched the second phase of FAME scheme, which provided further more incentives, and also it involved large, so it has an outlay of around 10,000 crore plus whatever residue amount which was allocated to the FAME the phase one of this scheme. So there is a huge outlay for this particular scheme, and it involves like several incentives. And so recently the government has been pushing creation of new charging infrastructure, and also developing standards required, and also government is working on battery swapping policies for electric vehicles, and also hydrogen power is being explored. So there are several initiatives being taken up by the government. So as I mentioned, the second phase of this FAME scheme, so it has an outlay, and it is mainly for four different things. So basically, first, the major part is the demand incentive. So that is like the large part of the outlay is allocated to this demand incentive, where uh, like direct incentives are given on the purchase of different vehicles. So as we can see, like this incentive is scaling with the amount of battery capacity. So if we look at let us say two-wheelers, so 15,000 rupees per kilowatt hour, and approximately like a two-wheeler needs about a 2 kilowatt hour of battery. So we can see about 30,000 uh, rupees of a total incentive may be available. So the electric vehicle prices have now become comparable with the conventional two-wheeler prices. And because of these attractive subsidies, now this is expected to provide like uh, substantial momentum, and it is like expected that the electric vehicle sales will pick up because of this scheme. The government is also working on opening up the market for creation of new uh, charging infrastructure. So along with the public sector companies, like new private sector uh, players are also being like invited in the creation of new charging infrastructure. Uh, so there are like these incentives and new policies which are reinforcing the shift towards more of electric vehicles in India. So Niti Aayog did a study to estimate what would be the potential benefits of this scheme if it were implemented as planned. So uh, whatever like the vehicles which are eligible under FAME, so which may be private uh, two-wheelers or four-wheelers or even buses. So the potential savings of about 5.4 million tons of oil equivalent are estimated, which would amount to a savings of about 17.2 thousand crores in the energy. So the oil import bill is expected to be like uh, substantially reduced because of this. So a substantial amount of reduction in the overall energy consumption, and about 170 petajoules, and about 7.4 million tons of CO2 emissions are expected to be reduced over the vehicle lifetime. Uh, so as we can see that these benefits are really promising, and a further study was done by Niti Aayog on like if we consider the scenario till 2030, if we try to project what could be the total energy savings and the amount of savings in the CO2 emissions. So they are very promising. So about uh, 840, uh, 846 million tons of CO2 emissions would be reduced, and the oil savings of about 474 million tons of oil equivalent. This is a huge number. Uh, so so we can see that this overall transition to electric mobility is very promising. So till now we have seen the overall background, and so in the current scenario, it is very important to study electric vehicles. Uh, so so finally, we come to our topic of automotive transmission. So before that, I just want to know if uh, any anyone has any questions or comments. So I'll just take a pause for a few seconds. So anyone has any feedback or comments to share? Am I going too fast or too slow? Any comments?
So it's just right.
Okay, sure. Yeah, sure. Then we'll move on to our actual topic. So, the automotive transmission, while designing them, we have some major functional requirements. So, if we have to list them, so I would like all of you to contribute in this discussion. So I hope so it should not be a monologue where I am just speaking. So it will become really boring. So I would like all of you to contribute in this. So if we are to think about, like, if you want to design a transmission for any particular vehicle, what are the factors that, like, we would consider? What different attributes would we consider? What are the different factors that are important when we if we want to design a transmission? Any guesses? Any ideas?
The speed and torque which are to be supplied to the wheels.
Okay. So in this, so can you elaborate more on that?
So while designing the transmission, if we want more torque, then we'll have to have larger gears, and
Okay.
we can have different components like torque converter, and we can use
Okay.
transmissions like CVT, which amplify torque and make it easier for the power unit to apply the torque.
Okay.
And
Right.
for faster speeds, we need lower ratios, and for faster shifting, we can use automatic transmissions like DCT and AMT.
Okay. Okay, great. So you have actually shared a lot of so since you mentioned a lot of options, so like you mentioned basically one is like the conventional type of transmissions. Um, then you mentioned automatic transmissions. Then you also mentioned CVT. Uh, so all of them, and you also mentioned like DCT, right? So
Yes,
so
sir.
all
I'd
of them
also
are different, right? Yeah, yeah.
and
Please go ahead.
I would like to also mention planetary gearbox.
Sorry,
Planetary gearbox, sir.
planetary gears. Okay, fine. Right. So planetary gears can be used in any of the transmission concepts, but yeah, okay, fine. Yeah, fine. So these are different options, like technology options, you can say. So if we want to, say, like, let us say if you want to design a passenger car or electric bus or whatever. So how would we decide, like, what we want? What would be our objective? Like, what we'll be looking for in like while designing a transmission? Like very basic things, like think about, like, uh, why would we need a transmission at all? Like, or like how do we select, or like on what basis do we select, like, each of these technology options? Uh,
There are various factors like first of all, the uh, pacing factor is the cost of the transmission.
right,
It
cost.
depends
Okay.
upon what type of vehicle we'll be using, and typically commercial vehicles have need higher torques, so
Okay.
they might prefer using spur gears,
Okay.
and so that could be included in planetary as well as conventional type of gearboxes. Automatic transmission vehicles which tend to remove shifting options, so they can use CVT. So scooters basically use CVT. Then automatic transmission is also used in sports cars, and AMT is used in normal cars as well for ease of driving.
Okay.
And DCT is also used in sports and racing vehicles.
Sure. Yeah. Yeah. Thanks for contributing, Sumit. Sumit, right?
Yes, sir.
Yeah. Sure, good. So I think you have, so you are, yeah. So I was looking for something like this, like factors like cost, or one factor may be efficiency. So so we need to have a high efficiency transmission. Yeah. So uh, if we have to look at yeah. So if we have to look at the different functional requirements of transmission, so we can probably come up with some of these factors which have been listed out. Some of you already covered, like high efficiency or cost, or so you also covered some applications. So basically, we need uh, a fuel efficient way uh, to basically transmit power from the source to the load. So basically, this is the major part of the transmission design. Like this is the major requirement. So and we'll also be mainly focusing on this in this particular unit. So how do we efficiently transmit power from the source to the load for different operating conditions? Uh, there are other factors like reliability or ease of operation. So as you mentioned, like so AMT for ease of operation, like if we have to map it to that uh, particular factor, like even DCT or AMT or AT, whatever for that matter. So they involve like minimal effort from the driver. So they involve a lot of ease of operation, but they may not always be reliable, or they may not have may not be very cost effective. So DCT is like basically dual clutch transmission. So if I'm not sure about whether others are aware of this technology. So it's an expensive technology, although it provides very smooth shifting between gears. So and automatic transmissions involve torque converters, which basically they are not very highly efficient. So they involve a lot of losses and heat generation. So there are factors like this. So um, the automatic transmission may also become bulky. Even dual clutch transmissions may become bulky. Uh, so there are different factors like this. So the key factor is basically how do we this the factor basically fuel efficient torque conversion. So if there is a certain uh, torque and speed requirement at the wheels, so or basically or power versus power and vehicle speed requirement at the wheels, and there is a certain source, maybe it may be IC engine or electric motor or any prime movers for that matter. So what is the torque and speed that at which the prime mover, basically the IC engine or the electric motor, should operate? Uh, so that for every power versus vehicle speed requirement, we get the appropriate value of torque and speed such that the source operates efficiently, and we also get the required uh, power and vehicle speed. So if we look at the typical power source characteristics, like if we have to imagine an ideal source of power, uh, we would like to have the entire maximum rated power being available throughout the entire speed range. Uh, and if you look at the corresponding torque versus speed, so constant power would imply torque into speed. So power is basically torque into speed. So torque into omega, which is the angular speed of the wheel. So that is constant. So so basically that would mean that torque is equal to some constant by omega. So if we look at the torque profile on a torque versus speed map, so then we can see that this is a hyperbolic kind of a profile. So uh, yeah, sorry for the poor writing. Uh, but so there is a certain limit of the because of the interaction between the tire and the road. There is a limit to which the wheel can or the tire can take up a transmit torque. It is governed by the adhesion limit. We will see this term later on. So basically, we just have to note that there is a limit, certain maximum torque which the wheel can transmit, which depends on the tire material and the road material or the road and the nature of the road, and whether like what are the basically operating conditions in that contact region between the tire and ground. So if we limit the torque to a certain value, so with increasing speed, we will see that the power will linearly increase from zero to the maximum power. So in this particular region, so which is basically this region. So up to this certain speed, we will observe like the power will increase linearly, and beyond that, let us say that the power remains constant. So this is what we would imagine like an ideal source of power would be. Uh, but if like correspondingly, if we look at the characteristics of an IC engine, so typically the power versus speed profile looks like this, uh, where it has like a power versus speed characteristic where which is like not constant over the speed range. There are also certain minimum and maximum speed limits depending on whether like the IC engine is not able to operate below a certain speed, and also it is not recommended to run the IC engine above a certain speed. So and if you see that the power versus speed or torque versus speed profile, it is like non-linear, and so we see that the torque or power is maximum in a very small speed range. So basically, if we compare the characteristics of the IC engine, they are like deviating significantly from the ideal power source. So is this particular part understood? Any doubts regarding this? Uh, yeah. So if this is understood, so then basically conventional vehicles are largely utilizes IC engines for as their power source. So if we have to answer this particular questions, so why do vehicles need a transmission at all? So we looked at the characteristics of an ideal power source and that of an IC engine. And if we have to visualize what is the function of a transmission, and if we have to answer this question, so what do you think is the reason? Like why do we have a transmission at all in a vehicle?
In conventional
Any ideas?
vehicles,
Yeah, sorry.
in conventional IC engine vehicles, the engine does not have the maximum torque at the start of the vehicle because it
Okay.
gains torque at a higher speed. So to
Okay.
start the vehicle from zero, we need to have some torque multiplication
Okay.
to propel the weight of the vehicle. So that is why we need a large gear, and
Okay.
large gear cannot sustain like it cannot take us to higher speeds. It has some limitation in speed.
Okay.
So that is why we need shorter gears as well. So that is why we need multiple ratios in an IC engine. As in case of motor, we need to reduce the size of the motor as is possible. So for the required torque, we can take the least size of motor by using a single gear transmission, or we can also use CVT transmission. So that is why the most important thing is that we need torque multiplication in transmissions.
Okay, yeah, I actually missed some. I could not hear you very clearly. So can you please repeat, like if you don't mind? So can you repeat
Yes,
what you just said? Yeah.
yes. So the primary reason in IC using a gearbox in IC engine vehicles is that the engine cannot provide its maximum torque at the slowest speed, which is
Okay.
basically when we are starting. So we need a large gear to multiply the torque from coming from the IC engine to propel the vehicle from start. And since the large gear cannot take us to higher speeds, we
Right.
need a shorter gear. So that is why we need multiple gears in an IC engine vehicle to satisfy
Okay.
the requirement of the curve of the driver. And in electric vehicles, we need it to reduce the size of the motor for the given
Okay.
torque.
Okay.
Yes,
So
and
right. So why do you think like the IC engine like maximum torque is not available at sorry. So why do you think like the IC engine maximum torque is not available from the starting?
so at the start, the speed is less, so even we get less power as much is required. So the force required is also less. Force obtained is also less from the engine at lower speeds.
Okay.
Even
Okay.
even the combustion is not the maximum at its maximum efficiency because efficiency rises at a bit higher speeds. So some of the fuel is just left out of combustion. Pressure is also
Okay.
less in the cylinder.
Okay. Fine. Uh, and what do you think like about so as you said if you use a very high gear we get a boost initially but uh, like we are not able to increase the vehicle speed beyond a certain limit, right? So so why do we so there is a certain limit, right? Like on the engine speed. So why is there a limit on the like engine speed?
So at higher speeds, engine starts overheating because of higher friction, and the valves and valve timing cannot be achieved at higher speeds. And valve timing and spark timing, injection timing, these are critical considerations for an engine. So after certain speeds, valve timing is difficult to achieve, and also there can be knocking phenomena. So that is why we need to limit the engine speed up to a certain extent.
Okay, great. So what about the others? Like I would invite others like asking like other than Sumed who like people also to contribute. So this was Sumed, right? Sumed itself, right?
Yes, sir.
Okay. So what about the others? Like uh, Sumed has several covered like several aspects. Like so with respect to conventional vehicles, like so he has described like the characteristics of IC engines uh, and yeah, if we have to justify like the need of a transmission, so like what do you think like are the uh, other factors? Any ideas? So like uh, I think Sumit has talked about like the performance aspects, like basically getting the vehicle to move from start uh, and accelerating to higher speeds. So what about the fuel economy part or energy consumption part? Like so, so the transmission also has some role to play in that, right? So what do you think uh, is the role of a transmission in that? Any ideas?
So may I answer?
Yeah. Who is this?
Sumit.
Okay. Yeah. Go ahead.
So higher at higher speeds we get less fuel economy
Okay.
after a certain speed. So we cannot go at the maximum speed of an engine for longer periods. That will give us a
Okay.
very poor economy. So that is why we need to reduce the gear ratios so that we can run the engine at the best speeds possible. So transmission is designed according to that as well. So
Good.
whenever we shift to higher gears, we can run the engine at low RPMs, so we can get higher
Okay.
fuel efficiency.
Okay. Okay. Good. Okay. Very good. Fine. So I think Sumed has a very good understanding of transmission. So what about the others? Like, so are you able to visualize? So okay, fine. I think we had a good amount of discussion on this. So maybe we'll look at some of the aspects of. So I think Sumed has touched upon like several aspects. So if we look at what are the advantages of IC engines, so basically they have high power to weight ratio. So a small engine is able to produce quite a lot of power, and the energy storage, basically the fuel. So the source is fuel. So it needs a very compact amount of storage. So a fuel tank uh, carries a certain volume of fuel, and the amount of energy that we get out of a certain mass of a fuel, basically the calorific value, uh, if we uh, if we have to imagine that, so that is about 45 megajoules or so uh, per kilogram for maybe a petrol or diesel, something around that range. So it's huge amount of energy that is produced by a certain amount of mass. So that is a definite advantage of internal combustion engine. But it has some disadvantages. So basically, in terms of efficiency, so if we look at the ideal like thermodynamic cycle, like Carnot cycles also, so like there is a definite limit on the considering like all the processes are ideal, uh, the Carnot cycle efficiency, like Carnot is the ideal cycle that one would imagine. So that also limits, has a certain limit, probably around 50% or so. So the IC engine efficiency is around in that range of 30 to 40% of efficiency. There is a huge amount of energy that gets wasted. So so leaving that factor aside, in the context of transmissions design, so the disadvantages of IC engines are basically that, as Sumed has rightly mentioned, the IC engine is incapable of producing torque from rest. So at zero engine speed, it cannot produce uh, any torque. So there is a certain minimum speed, or basically the idle speed at which the engine has to operate. And so for the vehicle, so the IC engine is running at a certain, let us say, idle speed always, and it goes like accelerates further. And so for the vehicle to accelerate from zero speed, we need a certain some mechanism which can basically accommodate this. So the vehicle is the output side, and it is accelerating from zero speed to a certain speed, and the engine is, let us say, spinning from certain non-zero speed. So there is a speed difference, right? So which has to be, so let us say if we plot like some if we um, project the IC engine speed onto the wheel, and if we look at the wheel speed, so there is a certain time for which the speeds are going to be unequal, um, up to, so this speed variation has to be accommodated by some component. So that is basically the clutch. So the clutch takes up this, so using friction, it basically accelerates the vehicle using friction, and brings it up to the speed such that, so after a certain time the clutch gets locked. So basically the relative motion is slowed down, and then once the clutch is locked, uh, the whole thing moves together. Uh, So that is one requirement of a conventional powertrain. Then the maximum torque in an IC engine, it is available in a very narrow speed range. So there is a peak which lasts for a very small range of RPMs. Otherwise, it falls off quite rapidly. Uh, and if you also have to look at the fuel consumption characteristic, it strongly depends on where the engine is operating. Basically, what is the torque and speed. So uh, the efficiency of the engine is very sensitive to the torque and speed operating point. So if we also look at the power versus speed characteristic, so the maximum power is available towards the higher end of the engine speeds. So to utilize the maximum power, we have to run the engine at like very high speeds, probably towards the maximum speed limit. So if we operate the IC engine for a long period, so then there would be excess wear and there would be a lot of heat that could be generated due to a lot of friction. So the IC engine operation has to be avoided towards the higher speed range. So as Sumedh has already mentioned. So these are some factors or which so the IC engine has certain limitations, and so if we have to basically if we let us say if we do not use a transmission, so if we just uh, directly connect the IC engine with let us say if we have an IC engine uh, and if we connect a clutch and let us say let us say this block is the IC engine and this is let us say the clutch and and we also have certain let us say some single gear ratio between the clutch and the wheels. So let us say these are the wheels. So that it includes basically the differential and all these things. So basically there is a single gear ratio between the IC engine and the wheels. So so if we calculate what would be basically by multiplying the torque uh, of the IC engine output torque. So the torque of the IC engine into the gear ratio would be basically the torque that is available at the wheels, and the engine speed, let us say omega e. So r omega e basically r is the wheel radius, and omega e divided by basically the gear ratio. Let us say this is g. So that would be basically the uh, vehicle speed which we will see like considering this gear ratio. Yeah. Anyone wants to say anything? I heard someone say something. Yeah. So basically, this is the vehicle speed, and if we look at the torque at the wheels, so torque would be basically let us say T is the torque of the IC engine once the clutch is fully engaged. So T into G will be the torque that is available at the wheels. So now if we look at this particular plot that is shown over here, so which basically plots the tractive force or let us say or tractive torque, the torque required to propel the vehicle at a certain vehicle speed. So if we plot this with respect to the vehicle speed, so this is like called as traction hyperbola, basically as we mentioned. So for a certain power requirement, let us say if the vehicle has certain rated power of some, let us say P kilowatt. So then the power uh, divided by the vehicle speed will be basically the attractive force that is required. Uh, so then that would be basically like in terms of if we plot this force versus vehicle speed for a certain constant power requirement, which is equal to the engine rated power requirement. So then this would look like something like this. So this shaded region is basically the the points, like the envelope in which we will we'll need the power, or basically the so from zero power to that power. So this will be the points which will be enveloped by this hyperbola. This is basically the friction limit which I mentioned. So considering the limit of force that can be transmitted by the tires. So this region is the expected region of operation of any particular power source for that vehicle, considering its rated power and the rated and basically this vehicle speed over which the range of speeds over which the vehicle is expected to operate. So if we compare what will be available, considering if like there is no multiple gear transmission, so then the IC engine would be covering only this part of this hyperbola. And because of the lower speed limit, like basically the idle speed limit of the IC engine, it is not able to cover the speeds below this range, and above the speed range, it is not able to operate because of the concerns of heat and wear. So we basically see that because of absence of adequate gear ratios, we are not able to deliver power at these particular vehicle speeds in this range. And also, like if we have to provide this particular amount of force at this particular vehicle speed, so then this this amount of power will the IC engine will not be able to provide at this particular speed. So so then that's why we need to have multiple gear ratios. So in order to cover this particular envelope, uh, so this is, let us say, the rated power, uh, the hyperbola, if we plot this, and now if we try to superimpose on this particular plot, like if the IC engine was operating with multiple gear ratios, uh, so then now if we, let us say, consider like the gear ratios, like let us say the first gear, it the first gear ratio is generally the highest one. It's like meant to start the vehicle from rest, and then the higher, as we go on, like accelerating from lower to higher speeds, then we'll need progressively lower gear ratios. Uh, so then if we superimpose the torque versus speed characteristics in terms of, like if we map the engine speed, basically the maximum and minimum engine speed uh, for that particular gear ratio to the vehicle speed, or basically the wheel speed, considering that gear ratio, then we will get the envelope which is shown over here. So now we can see, if we compare to this figure over here, now this, with multiple gear ratios, we see that it is able to cover much more amount of this particular traction hyperbola region. So we are able to we are able to provide power at several points. So there are still some amount of regions which the IC engine fails to provide power. So these, let us say, these regions or this region, but still, like using more and more gear ratios, we will be able to cover more and more part of this envelope. Um, so, so that's how we are able to basically provide the required power at the required vehicle speed. So that's why we need a multiple uh, gear ratio transmission with in conventional vehicles. Uh, so has everyone understood this part? Is there anyone who has like not understood? Like, so does everyone understand how do we get this particular figure of the IC engine characteristics? Like like the torque versus speed, like versus vehicle speed. Is there anyone who does not understand this? So any doubts, or should we proceed? So basically, how do we get this particular this profile for every gear? Is that like as we did the calculation over here, we find the corresponding vehicle speed. Let us say V minimum is basically this R omega engine. So basically, the minimum speed limit of the IC engine by the particular gear ratio. Let us say G1 is the gear ratio in the first gear, and V maximum, let us say, is the maximum, like the maximum vehicle speed which it can run in this particular gear. So it will be R into omega engine maximum, basically the maximum speed of the IC engine, uh, divided by the gear ratio G1, let us say. So this will be the so this is the V minimum, and this is the V maximum for this particular gear. And similarly, if like for every gear ratio, so instead of G1 we use G2, G3, G4, whatever. Uh, so then we'll be able to calculate the corresponding minimum and maximum speeds, and also the intermediate speeds we can calculate for this curve. And similarly, we can calculate the torque using this particular equation. Instead of G1, like we'll use G1 or G2 or whatever. And then we'll get this particular curve. And for every gear, we'll be able to get this particular curve. And if we superimpose them, we'll get this particular envelope. So I hope everyone has understood this. So by increasing the number of gear ratios, like by using more and more gears, we can cover like most of the part of this particular envelope. Let us say if we use infinite gear ratios, then we would probably be covering like most of the particular traction hyperbola. So which is what is the idea of the continuously variable transmissions, or what is called as CVT. So which has the gear ratio varying in a continuous fashion. So there is no step. So here we have discrete gear ratios. So here, like in CVTs, we can vary the gear ratio in a continuous fashion. So there is a smooth transition between like different ratios. Uh, so then we do not find like much gap in this particular case like this. Although so this application might be like appearing to be very promising. So there are certain limitations of this technology, like the way we are able to achieve continuous variation in the gear ratios. So there are certain applications like in like the two-wheelers that we commonly drive, like Activa, like Honda Activa, they have these CVT kind of transmissions. So by depending on the accelerator pedal position, the CVT ratio will vary, and it will adjust its gear ratio accordingly. So we have seen like by using multiple gear ratios, we are able to cover this torque speed envelope substantially. Apart from that, uh, what the transmission provides us. So it basically provides us a flexibility or basically a choice to select uh, the engine operating point. Uh, so by using this particular choice, so we can place the IC engine point such that we are able to provide the required torque at the required vehicle speed, and we are also able to operate the IC engine in its like greater efficiency region. So let us take an example. So if we want to drive our vehicle at a speed, let us say 35 kilometers per hour. Let us say we are driving a car. So I hope all of you are able to visualize, like, or most of you are have learned how to drive a car. Uh, so let us say if we take a speed of, let us say, 35 kilometers per hour for a passenger car, which gear would we be normally operating the vehicle in?
In cities, we mostly operate in third, second, second or third gear.
Second or third. Okay. Okay. So why do you think we will be using these gears?
Those gears, the RPM of the engine is optimum to maintain a good economy and also get a decent power out of decent torque.
Okay. 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 Right. Right. So if we have to, so Sumit, you are on the right track. So if you can, like, uh, so let us say we this is the hyperbola which represents the power requirement in this particular case. Uh, so the transmission provides us, let us say, with these three options. So let us say at 35 kilometers per hour, we have the options of second, third, and fourth gear, right? So we can run the vehicle in second or third or fourth gear. So where do you think the operating point of the IC engine will lie? So which of these operating points corresponds to which of the gears? So can you tell me that?
So here's the second gear can be represented by the first point from the left.
You mean this one?
Yes, sir.
Do you think this is the second gear thing?
Yes, sir, because the speed is low and the torque is high, so it must be higher, lower gear.
So this is basically the torque produced by the IC engine, right? So this is
Okay, okay, okay,
please
sir.
note that. So
Yes.
okay, so
In that case,
we
it will
can,
be just the reverse.
so no, sorry, come again.
In that case, the first dot will be the fourth gear, then followed by third, and then the second gear.
This is third and this is second, right?
Yes, yes, sir.
Yeah, very good. Yeah, you are right. So you are right. So when we choose a higher gear ratio or a lower gear, so second gear, then to produce the same amount of torque at the wheel. So note that, let us say, for a constant like this speed, there is a certain corresponding torque versus speed requirement. So so let us say this is that particular, let us say, so if there were a common overlap region, so let us say this is the particular torque versus speed operating point, and then let us if we are able to operate it in the second gear or in third gear as well as fourth gear. So if we consider a higher gear ratio to deliver the same amount of torque at the wheels, the IC engine has to produce a lower torque, and for the same like higher gear ratio, uh, to produce this the same vehicle speed, the engine has to run at a higher speed. So that's how, like, so you are correct. So the engine is running at a higher speed over here and producing a lower torque. So that's why, like, in the second gear it will be somewhere here. If we look at the fourth gear, then the gear ratio is like much lower than the second. then the IC engine has to run at like a much lower speed for the required vehicle speed. But because of the lower torque multiplication factor, it has to produce a higher torque. So that's why it lies somewhere here. Now, if we look at the third gear, it is like placed at a somewhat sweet spot kind of thing. Like it is producing decent amount of torque, and it also is in somewhat of a like the middle range of the speeds. So it neither the engine would neither stall or it won't even overheat. So this is how like basically that so this would lead to better fuel consumption behavior. So that's how the transmission actually helps us in placing the IC engine operating point so that we are able to efficiently deliver the required power at the required speed. So is this concept understood? Any doubts? So here, like we have n discrete gear ratios. So like if if we might think that we can keep on increasing the number of gears so that we have so many choices. But then that has also certain limitations. Like that would like if we use like huge number of gears, so then it will be difficult for the driver also to select gears, and also it would complicate the transmission quite a bit, and that would also increase the cost quite a bit. So then like based on practical limitations, we select like the number of gear ratios required so that like uh, so that we are reasonably able to accommodate the entire torque and speed so that we can utilize the IC engine so that it covers the entire power and speed range. So if we look at the typical uh, characteristics of the conventional vehicle like the IC engine, if we so basically why I am going into the conventional vehicle kind of details is basically you probably might have learned all these things already, but in the context of transmissions for electric vehicles, I think it is very important to understand. So the earlier automotive transmissions which were designed for uh, conventional vehicles, what are the factors based on which they are designed? So the characteristics of the power source itself are so important that that is basically the basis on which the transmission of any vehicle is designed. So the transmission is designed to so that we can deliver the required torque at the required speed, and we also want to operate our power source as efficiently as possible. So then, based on the behavior of the power source, let us say IC engines in conventional vehicles, we will place basically the we will design the gear ratios such that in the typical operating range of the vehicle, we will be able to operate the IC engine in its most efficient torque and speed range, and also be able to uh, run the vehicle in its required power and speed, power versus vehicle speed map. So if we have to look at the typical characteristics of the IC engine, let us say like for different throttle fractions. So if we let us say like the accelerator pedal input from the driver, if it is it has some uh, direct mapping to the valve opening or basically the amount of fuel that is injected into the cylinder, and so basically the throttle and the driver accelerator pedal input have a direct relation. So if we look at how the behavior of the IC engine, torque and speed that is available in that particular, so considering a throttle opening of let us say 20%, then this is how the IC engine torque availability versus speed varies. So so we can see that the IC engine torque like varies quite a bit over the entire speed range, and like so for like smaller throttle inputs like less than 50%, the engine torque is actually dropping down quite rapidly below a certain above a certain speed range. So we see that basically the torque availability is quite fluctuating over the entire speed range. So then it is like critical to maintain the IC engine operating point within a certain range, uh, because then that would have a direct impact on the fuel consumption. So so if we have to comment on why this, let us say if we look at this particular throttle behavior like for 10% or let us say 5%. So at this very low throttle, the IC engine torque goes down rapidly to zero at like up to a certain speed. So can anyone you know explain this? Like why do we go down to zero? Or why is the behavior like this? So why is the IC engine behavior like this? Like why does the torque drop down as we increase the speed? Anyone like can answer that? So the plot on the left is for spark ignition engine. This is like this part, this is for SI engine, spark ignition, and the right hand side plot is for a compression ignition engine, or basically a diesel engine. So can anyone tell like uh, what is the reason for that? Like why does the torque drop rapidly? So basically we know
Sometimes at higher speeds,
yeah.
at higher speeds, the very high speeds, the combustion quality reduces a bit, and
Okay.
we cannot get as much pressure at that point. So for extra torque, uh, higher pressure is very essential.
Okay. Okay. Okay.
We tend to lose higher pressure at higher speed because of the fact that the engine valves are mostly open, because they cannot cope up with the engine speed at higher speeds.
Okay. So okay, fine. Can you comment like anything else? Like what about uh, so you this is basically brake torque, right? So so there is something called as indicated power, right? So indicated power is brake power plus something, right? What is that something?
There are frictional losses.
Yeah, so there is friction power, right?
Also takes away losses from some.
Right, right.
And
So as you
just
mentioned, so this brake power or basically the indicated power is something that is basically because of the thermodynamic cycle, like because of the pressure, so pressure volume work that we get. So there is a certain expansion of the gas, that corresponds to a certain pressure volume work, right? So then that is the indicated power. So that may drop down, as you said, because of, like, we are not able to generate that much pressure and all. And there is also friction power. So with increasing speed, the friction torque will remain constant because it is like some mu into n. So that, let us say, like, mu into some normal reaction. So then that friction force is constant. So that into the, let us say, radius or whatever. So basically the friction torque is something that is constant. So torque into omega is basically the engine speed. So the engine is like the piston is, sliding along the walls of the cylinder. So then the torque generated due to friction is depending on the speed. So with higher speeds, so it will dissipate energy at a much higher rate. So then the friction power is something that will also rapidly bring down this brake power. So that's how, like, you rapidly, we see that this, rapidly goes down with speed, right? So do you agree with that?
Yes, sir.
Yeah. So anyway, so so this is for the spark ignition engine and the diesel engine. So we can see, like, if we compare the behaviors, so the spark ignition engine has a, like, greater speed operation range. We can see, like, about 5,000 or 6,000 RPM. Uh, and whereas if we see the compression ignition engine or diesel engine, so it has a slightly lesser uh, speed range of operation. But if we see the torque range, so it is able to produce torque over a much greater range. Basically, the CI engine. So it has a greater torque spread, whereas the SI engine has a greater speed spread. So depending on these specific behaviors of the IC engine, when we are using, so depending on that, so that has important implications on the transmission design because uh, we like if the speed region, like speed spread shrinks, so then we may need to have more gear ratios to be able to accommodate more number of speeds, or if the speed spread is like quite a bit, so then we may not need lot of gear ratios for that, something like that. So now, if we now, like, come to electric vehicles, which are primarily powered by electric motors. Uh, so then, if we have to compare the typical behavior of the IC engine versus that of an electric motor, so we saw the ideal torque speed and power speed kind of profiles. Um, so we can see that the torque versus speed or power versus speed here. So this is the typical torque and speed and power versus speed characteristics for a motor, electric motor. So this is the maximum torque it can produce with increasing speed, and this is the maximum power it can produce. So we can see that this matches quite a bit to the kind of ideal power source characteristic that we would have imagined, whereas the IC engine is like deviating from that. So there is a certain amount of speed up to which is called as the base speed, up to which the electric motor can provide high torque, and an important advantage that the electric motor has. So it can produce very high torque even at zero speed. So the requirement of a clutch, let us say, to be able to accommodate uh, that the engine cannot go below the idle speed. So here we do not need that because we can directly provide the entire maximum torque at very low speeds. So then that would have helped the vehicle in its acceleration characteristics. We will see that later. So that's a definite advantage that the electric motor has over an IC engine. Now, if we see that the torque actually goes down as we with increasing speeds, but like so, once the vehicle gets moving, our torque requirement also reduces. So then that does not uh, lead to a major disadvantage. So, but our almost entire rated power is available. So beyond this base speed up to the maximum speed of the motor, we largely see that the full maximum power is available from the electric motor. So, so unlike an IC engine where we have a very small range of speeds, like here, where we can we'll get maximum power. Here we have the entire speed range where we can actually draw the maximum power from the electric motor. So and also for the torque, like we can see that there is a small range in which we get very high torque from the IC engine. So we need to keep the IC engine in this speed range so that we can get with optimum torque like that. So is this part understood? Shall
Yes,
we
sir.
proceed? Okay. Now, see, we have seen the maximum torque and maximum power characteristics. Now, if we look at the aspect of efficiency, uh, so generally for an IC engine, we will report its fuel efficiency characteristics in terms of brake specific fuel consumption maps or basically contours, which are basically some kind of shapes like this, which is shown over here. So these lines correspond to constant brake specific fuel consumptions lines. So can anyone tell me what is brake specific fuel consumption?
So it is the equivalent fuel consumption for a unit brake power, unit of brake power.
Okay. So can you tell me like how will you calculate what what is the equation like to calculate the brake specific fuel consumption? Or let us say what is the
Okay.
unit, so that will probably become easier to
It,
Grams per
sure, but it
kilowatt.
is
grams per.
Kilowatt hour.
kilowatt.
Okay. Okay, fine. Grams per kilowatt hour. Okay, fine. So if we say like this is equivalent to grams per second divided by kilowatt hour per second. So grams per second is some rate of mass flow, whereas this kilowatt hour per second is basically the rate at which energy is being delivered. So basically this is power. So mass flow rate or basically fuel consumption rate m dot, let us say, that divided by the brake power. So that is basically the brake specific fuel consumption. So so if we so if we just multiply this mass flow rate into the calorific value CV, let us say. So then this is basically the energy input from the fuel, and brake power is basically the energy that we like get as the output. So so the brake power divided by this mass flow rate into the calorific value is basically the efficiency or thermal efficiency of the IC engine. So there is a direct relation between through the calorific value. There is a direct relation between the brake specific fuel consumption and the efficiency. So so wherever we see so this is basically, so the efficiency, let us say eta, is brake power divided by this mass flow rate into calorific value, so which is basically 1 upon brake specific fuel consumption, so into calorific value, right? So then it's inversely proportional. So less lesser the brake specific fuel consumption, greater is the efficiency. So then so we, as we go inside these these contours, so here we see that the brake specific fuel consumption is the least. So these values are written, so they represent the constant brake specific consumption, specific fuel consumption. So we see that in this region, the IC engine brake specific fuel consumption is the least. So that's where the region where the efficiency is maximum. So the IC engine should operate somewhere here in this, let us say, region of optimum efficiency. So this is kind of the sweet spot that the IC engine should always operate in. But whereas like practically it may not be possible to have the IC engine operating always within this narrow speed range. So then we can actually plot a line of minimum fuel consumption over the entire speed range. So this particular line, so which represents the, so like for a certain given vehicle speed, it will cut across these different contours, right? So then there will be a certain uh, torque at which, for the given vehicle speed, the brake specific fuel consumption is the minimum. So for every engine speed, if we calculate the corresponding torque at which the brake specific fuel consumption is the least, so then we will get this particular line. So anyway, basically, the only important part is that we have a narrow region of high efficiency, and as we move away from this particular region, the efficiency will drop down very fast. On the other hand, if we look at the efficiency characteristics of electric motors, we can see that its peak efficiency zone is about, let us say, 90% or even more than that. So with the current motor technology, we can get efficiency as high as 98% or 99% as well. And as we move away from this efficiency region, so the drop in efficiency is not very significant. So if we, let us say, increase like the motor speed from, let us say, by from 1000 to 2500 rpm, so then the drop in efficiency is like, not very significant, let us say from 90% to 83%. So it's not as significant as we would imagine in an IC engine. Like, here it is 250, and if we just move away from here up to, let us say, like something like, from 2000 to 4500. Um, so then the specific fuel consumption for producing the same amount of power will be much higher. Like if we move away from that particular region, so then there is a significant impact on the efficiency of the IC engine, which is like much less significant in an electric motor. So this is an important point to note. So maintaining the IC engine torque and speed within a certain narrow range is a definite requirement that the transmission has to satisfy. But in an electric motor, this particular requirement may not always be that critical. So another important point to note is that the IC engine generally has maximum speed up to, let us say, 4,000 or 5,000 or even sometimes up to 6,000 RPM. But electric motors nowadays, they can be uh, made to operate at very, very high speeds. So there are electric motors which can run even up to 20,000 RPM. So they can cover a huge range of torque and speeds. Uh, so and they can also, like, there won't be much loss of an efficiency if we change the operating point uh, away from that particular sweet spot region. So so then the transmission that we would design for a vehicle which uses an electric motor would have different requirements as compared to IC engine. So that is the important point to realize over here. So has everyone understood up to this point?
Yes, sir.
Okay. Yeah. So now, as we were saying, like earlier, we were discussing that uh, we saw that like with multiple gear ratios, how we can cover the torque versus vehicle speed range. So now, with an electric motor, so this is, let us say, represents like torque or force at, like, the force between the wheels and the road, or the force that is transmitted by the tires. Uh, and so this versus the vehicle speed. So if we look at this typical characteristic, uh, so for an IC engine along with a 4-speed transmission, this is how it would probably look like. On the other hand, if we use an electric motor which can uh, like combined with a single speed transmission, it can also substantially cover this whole region of torque, or basically force versus vehicle speed region, even with by using just a single gear ratio. So with this uh, single gear ratio, we may not be always operating in the best efficiency region of the motor, but the loss in efficiency that we get uh, like because of that is not as significant as an IC engine. And so with by using this single speed transmission, we can also deliver the required power like this. So this is just a particular example. This may not be always possible in every vehicle, but this is a fact to realize that we may not always need multiple gear ratios along with electric motors to provide the required power. So any doubts on this? Any comments? So now if we have to compare between an conventional and an pure electric powertrain, let us say uh, if we have an IC engine driven powertrain, so typically it would look like the way it is shown in the figure over here. This is typically what is called as rear wheel drive. Uh, so we have like the forward like axle as well as rear axles. So the power of the IC engine is delivered to the rear axles through so there is a clutch transmission, and the output of the transmission is connected to a propeller shaft, So the engine is generally in a passenger car, it is placed in the front, and this propeller shaft uh, goes from the output of the transmission from the front to the rear axle, uh, and then this shaft goes to the differential, and the differential output is connected to the axles, like the wheels. So that is the typical layout of a so-called rear-wheel drive conventional powertrain. So what kind of typical layouts like we would expect in an electric powertrain? So somewhat like this. Let us say, so it won't be very different. So it will basically take, like the way in a conventional vehicle, the accelerator and brake pedal inputs from the driver would be taken. So there would be a vehicle controller that interprets these signals, and it sends uh, appropriate signals to the power converter. So it sends the signal of how much current to draw from the electric motor. Uh, so the electric motor is connected to an energy source. So this may be a battery, or maybe a fuel cell, or ultra capacitor, or combinations of these. It can be anything. So the vehicle controller, based on the driver's input signals, so there is an energy management unit which basically decides based on the driving conditions and the driver inputs. So the driving conditions meaning what is the inclination of the road, or uh, you know uh, or the current temperature. So what is the current battery temperature, or things like that. So based on that, it will decide how much power to draw from the energy source, and it will send appropriate signals to the energy source, and so some part of the energy is supplied to the electric motor, and some part of the energy is provided to this auxiliary power supply. So these are basically the accessories. So it may comprise of the power steering unit, or which is called as hotel climate, or basically the air conditioning system. So generally in conventional vehicles, it is run by, so there is a belt drive available at one of the end of the crankshaft. So that drives all the accessories like air conditioning, compressor, the alternator, uh, and there is a starter motor which is connected, which is needed to rotate the crankshaft for starting the IC engine. So some of these things get eliminated in an electric vehicle. So there is no starter motor that is required, and the air conditioning compressor is driven by the battery itself, or whatever electrical energy source. And this electric motor may be connected to a mechanical transmission, which is connected to the wheels. So this is like a basic electric vehicle layout. So what can we expect like a typical electric vehicle, powertrain? So I hope everyone understands this word called powertrain. So powertrain basically means the way in which different components are connected from the energy source up to the load, or basically the fuel tank to the wheels, or maybe the battery to the wheels in an electric vehicle. So what can be the different layouts or configurations that we can expect? So, so let us say if we consider this figure A, which is shown over here. So we can have probably a single motor along with a clutch, uh, and maybe a multiple speed, like multiple ratio gearbox, which is connected to the differential, which is called the D, and which is connected to the wheels. So this may be a rear wheel drive or front wheel drive. Alternatively, we may probably be able to eliminate the clutch by using like the motor, by controlling the motor appropriately during gear shifting. We may be able to eliminate the clutch as well. Uh, so that may be another possible layout which is shown in this figure B. If we look at the figure C, here we may connect the motor in line with the axle to which the power is being supplied. So here this arrangement becomes very compact. So if we mount the motor along with some fixed gear ratio um, to the differential, so then the whole arrangement becomes very compact, and we are able to save a lot of space in this kind of arrangement. Alternatively, if we look at this particular configuration which is shown in the figure D, uh, so here we can actually eliminate the differential by having two separate motors. Uh, so by using a motor along with some fixed gear, so we can have uh, this particular layout. So by so in the driven axle, so it has separate motors required, which are like we need to provide power to them separately. So by that we can eliminate the differential this way by using two different motors along with appropriate gear ratios. So by the way, what is the function of a differential?
Primary function is to split the power in 90 degrees, and secondary, but important function is to allow the wheels to rotate at different speeds while the vehicle is turning.
Right, right. Yeah, so definitely. So here in this particular layout, which is shown over here, we need to control the motor speeds very carefully, so that while turning, uh, the vehicle is able to turn safely without the wheels skidding or slipping. So we can also think of a similar kind of a layout where we eliminate the differential, so where this is somewhat like an in-wheel kind of motor. So the motor is kind of mounted somewhat like adjacent to the wheel itself, and there is like a gear ratio, a gear reduction within the wheel itself. Uh, and this arrangement is even more compact. Uh, this actually saves a lot of space, and it saves a lot of space and cost as well. So, but the control of the motor is very complex, and this has also a definite limitation that uh, the thermal management of this motor. So because this is the motor gets overheated, so the thermal management and cooling of the motor is a very difficult job in these kind of uh, layouts. And we also may need very high torque motors. So like if we consider the layout over here, so here there is no gearing at all. So the motor is directly mounted within the wheels, which is called as like hub motor or something like that. So the uh, the stator of the motor is kind of connected to the wheel rim, and the rotor, the commonly called rotor of the motor, is mounted on the axle, and then we are able to directly provide power to the wheels by mounting the motor in that wheel hub itself. So then that may seem like very simple, and but it's quite challenging to implement because we need a very high torque motor, because there is no gear ratio that is available. So we need like very high torque versus very high vehicle speed range of operation. It may be challenging to implement in any particular vehicle. So these are some typical layouts, and so there may be even more layouts possible. So different companies have explored different concepts. So companies like Tesla, Porsche, and other OEMs, like they have all explored different configurations. So we'll explore them in our later sessions. So like so it's our like the different particular configurations may be possible depending on the requirement. So and many companies have innovated in this particular region, like this space. Uh, they have come up with very interesting layouts and different ways by which they can meet the performance and efficiency requirements. So we'll discuss them in the further session. So I would like to close today's session. And before that, like before we close, I uh, we'll have an activity like so that I hope this activity would be interesting for all of you. So you can form groups of 4 or 5 people. So how many people are there in the class?
So we have around 25 students for honors course, near about 35 students for MTech, and for PGDM, near about same, 30-35.
Okay. Okay. So
So
okay. So in this particular lecture, I see 30 participants. So I
yes,
think it's excluding the two of us, I think there are 28. So
yes.
probably
There
uh,
were 40 people before, like for 10-15 minutes. So
okay. Yeah, fine. So
this activity we can make compulsory for honor students, and left others they can do as per their interest.
okay. Okay, sir. Fine.
Yes. And,
Yeah. So I will suggest. Yeah. Yeah. Yeah.
yeah.
Okay. Fine.
So Parth, so tomorrow we will meet in the morning, right?
Yeah. Yes, sir.
8 o'clock.
Yeah. So,
Okay.
sir, can we start around 8:30 or 8:15, something like that?
Yes, yes, no problem. We can start at 8:30, no problem.
Okay.
Right. So this is to inform you all that tomorrow morning we are meeting at 8:30. And then maybe day after tomorrow or after that we will see as per convenience of Parth and students as well. So like over to you, Parth.
Sure, sir. Thank you. So yeah, before we close, I wanted to suggest an activity. So since we have discussed like different, the comparison of conventional and electric vehicles. So let us do an activity. So we will divide ourselves among groups of, let us say, 4 or 5 people, and so we will pick, let us say, a car or bus application. So we can, consider any model of which has. So many companies have a conventional model as well as electric model of the same vehicle. So especially the Indian OEMs have. Uh, so there may be other OEMs, overseas as well. So so we can pick up a car or bus which has like conventional as well as EV, and we'll make a comparison of them like based on these metrics, like let us say rated power, maximum torque, what is the maximum speed, what are the typical energy consumption characteristics, what are the mileage or range figures that are reported, what is the acceleration performance, so which is generally reported as the time required for the vehicle to accelerate uh, from 0 to 100 kilometers per hour or something like that. What is the layout of the powertrain? How are the different components connected? And most importantly, what are the kinds of transmissions that they use? So between the conventional vehicle and the electric vehicle, uh, are they using the same transmissions or are they different? And why are they maybe different? So please try to collect as much information as possible. And I suggest that you prepare maybe a one slide or so on that, uh, comparing the electric and conventional models based on these parameters. So try to get like as much information as possible, even the transmission gear ratios if possible, if you get, and then we'll have a discussion in class. So basically, this activity will help us understand what are the current trends in the the market, like for electric vehicles, what are the typical types of powertrain layouts that are being explored, and what are the kind of transmissions that they use. Uh, and we'll be also able to understand like what like based on the application, what are the different concepts that companies have considered. So I hope you find this activity interesting and useful. So I recommend you, all of you, to please try out this activity. So, and maybe probably in the next or next to next session, we may have we'll have a discussion on this particular aspect. So that's from my side. So all of those who attended today's session, so thank you for patiently listening, and I hope it was useful for you. So any particular comments or feedback for me, or any questions?
Okay, so if there is no any question or doubt, we can stop.
Sure. So I think we can close today's
Yes,
session.
yes, yes.
So
Thank you.
thank
We
you
will
all.
meet tomorrow morning. Okay.
Okay. Thank you.